very happy of this conference, very, very interesting, but I'm also quite tired. So I have the pleasant duty to terminate the conference, but my first task is the following. At the end of my talk, you should be no more tired and no less happy. So I hope it will be so. My argument is elegant by design. It refers to the design which never had been, because it was designed, it was built in 10 days, so they say. JavaScript was designed and built in 10 days of the JavaScript language. This is me. Okay, I wrote a bunch of things I did in my life. These are milestones in my life, but essentially, currently, I am IT expert at the GSE, which is an Italian government institution dealing with renewable energies. I work in the IT department doing stuff of various kind, technical stuff. And I am a mathematician. I never got a class in computer science, but at a certain point in my life, I turned to computer science. And in 2013, I had a daughter of 3 years old, and I wanted to build for her an app. I had an iPhone. I wanted her to draw on my iPhone. And I tried to program the app. It was a nightmare, so I decided to use HTML5 plus JavaScript. At the time, I was a project manager in IT projects. So I knew about JavaScript because my teams, my colleagues used it to essentially to do validation of web form. We were in 2013. And I used it to make a single page application which ran very well. My daughter was very happy about that. You can download it at the QR code. So I decided to learn a bit better JavaScript. And I don't know you, but to learn languages, that's why I know very few languages. Usually to learn languages, the best is to try to write a compiler for the language or an interpreter. So you really have to understand properly the semantics of the language, and you should write the interpreter or compiler in the language itself. That's the non plus ultra to understand the language. So first of all, I want to talk you how this is possible, because this is one of the stunning, of the amazing characteristics of programming languages. They can describe themselves. That's not trivial. For us, perhaps it's trivial, but that's not trivial. Not any system can describe itself. The history is quite long, but let's say, I hope someone will get the title of this slide is the title of a famous movie by Luis Buñuel, which was a Spanish director. And programming languages are discrete objects, are formal systems. They are different from human languages. Human languages are ambiguous, are difficult to learn, and whatever. Instead, programming languages are formal systems. The guy in the picture is Noam Chomsky. He's almost 100 years. I think next year he will be 100. And he's the guy who invented the generative syntax, which is the linguistic theory underlying the theory of compiling programming languages. He did it in the 50s. So in the 60s, we had a compiler for whatever language we want. And he stressed the relationship between languages and automata. There are some languages which can be generated by some automata. For example, a finite state automata can generate only regular expressions, regular languages, not any kind of language. To generate any kind of language, you need something as powerful as a Turing machine. Okay? So there is a hierarchy of languages and the corresponding automata which can generate them. That was the great contribution of this linguist and philosopher to computer science. But the history, it's started before. The guy in the picture with those terrible birds is better was Gottlob Frege. He was a German philosopher. He was the guy who invented predicate calculus, which is the typical formal system used in logic. But he invented not a textual language, he invented a graphic language he called Begriffsschrift. Here you see a sample of this Begriffsschrift. It's even difficult to pronounce the name of the language, so it's totally impossible to understand the language. But nevertheless, it hides the very idea of predicate calculus. Next, at the end of the 18th century and the beginning of 19th century, Giuseppe Peano, an Italian guy, wrote Formulaire de Mathématiques. He wanted to express all mathematics in formal terms. He invented a formal language to express mathematics. Here are his celebrated 5 Peano axioms for natural numbers. By means of these axioms, he could deduce any theorem about arithmetics. And if you see, this is a textual language. It uses some strange symbols. Some symbols are not so strange. For instance, the 0 axioms is n naught belongs to classes, which means the set of natural numbers is a class, is a set. And that epsilon, which is a Greek letter, nowadays use it to say that an element belongs to a set. And it was invented by Peano. Other symbols may be more cumbersome. But anyway, the important stuff is that he gave a textual language, not a graphical one. Okay? This is an example of formal language. But okay, the formal language par excellence is the predicate calculus, which was invented by David Hilbert, great mathematician. He wrote formulas in a way which is very familiar, because this is the very notation uses today in logic. It was invented in the 20s, of the last of the 20th century, of course. So 100 years ago, he invented predicate calculus. An old programming language called Prolog, maybe someone of you have heard this term, was just a translation in the ASCII character set of the Hilbert predicate calculus. So this is a very important and is the first completely rigorous formalized language ever. This is the ancestor of any formal language. So also of any programming language. Now, I expect you to know who these 2 guys are. Let's see, who is this guy on your right? Alan Turing, Alan Matheson Turing. Okay, now he's running. At the time they were not programmed to run, so he ran himself, but he was a runner. This guy, you should know it. This is Alonzo Church. He invented lambda calculus. If today you call a function a lambda, it's because he invented this symbol. As he called the function Donald Duck, today you will say, we have a Donald Duck to plug into an expression, okay? He invented lambda calculus before computers to express in a precise way algorithms. The both guys, actually, Turing did his PhD thesis under the supervision of Church in Princeton. And these 2 guys gave the first formal definition of an algorithm. So they started computer science somehow. Turing did that in terms of machine, of automata, of Turing machines. Church in terms of functions. So here stems the distinction between imperative languages and functional languages, before computers were ever invented. The guy in the picture is Konrad Zuse. He's credited to have invented the first computer in 1943 in Germany. The computer was destroyed during the Second World War, and after the war, Germans were forbidden to build other computers because they lose badly the war, so they had some constraint, restrictions on technology. Notice that the programming language he invented to program is Z3. The name of the computer was Z3. This plain calcul was somewhat resembling Frege Begriffsschrift. So it seemed to be a German stuff, this of using diagrams instead of text. But this is credited to be the first language ever programmed on a computer. Now, so far as the history, the prehistory of programming language is concerned. Next, we have another element very important in any language and in computer science, which is recursion. The concept of recursion was essentially invented by these two guys. The one on the left is Richard Dedekind. He proved the theorem, the recursion theorem. Each time you use a recursive function, you trust this theorem because it's by this theorem that the function does not go always in infinite loop. And he is Cantor. He used recursion to prove some strange things, strange fact about sets, but I don't want to talk about that. This is a recursive construction of a curve which will eventually, a continuous curve, which will eventually fill a square. This was did by Peano and Hilbert, and it's very weird because it's difficult to imagine a curve, a one-dimensional thing, which can fill all a two-dimensional set, a square, but actually it is so. So recursion is very powerful and counterintuitive. It was invented by this guy. Why do we deal with recursion? Because the description of programming languages, we saw this yesterday with Marco talk, the description of programming languages, or so to say, the grammars of programming languages are inherently recursive. This is a very toy grammar of an expression. I wrote in an old-fashioned way. It's called BNF, this notation. Was invented in the 60s to describe programming languages. HTML stems from SGML, which stems from this notation. That's why we have the acute parenthesis. So an expression, expr, can be defined as a value or a value followed by an operator followed by another expression. In this way, we can express the indefinite iteration of values connected by operators by means of recursive definition. The definition makes sense because we have one case, the first one, in which there is no recursion. Okay? It can be a single value or a value iterated by other expressions. The same is true to describe what a value is, because a value can be an expression between parentheses. A number can be defined as a string of digits, which can be defined recursively in this way. Okay? Now, these guys that you see, okay, my wife say, when I come to this conference, my wife says, oh, you are going in that place where there are all those odd people, referring to us because we are dressed like that. But I show her this photo. They have a jacket and tie, but they are odd too. Look at the faces. You know who these guys were? On the upper left, we see John McCarthy. John McCarthy invented Lisp, wrote the first garbage collector in the early 60s. He invented the term artificial intelligence in 1956. That's our very important people for us. This one is Alan Perlis. You know the guy. He was very important computer scientist. He wrote beautiful sentences. For instance, you shouldn't use so much syntactic sugar because it causes cancer of the semicolon, for instance. This is one of these sentences of Alan Perlis. This is John Bacchus invented Fortran, invented a lot of things. This is Peter Nauer, a Danish computer scientist, a great computer scientist, and so on. Well, they invented this notation. So in the 60s, they had these two concepts, languages and machines, which can generate languages as formal systems, and recursion. If you put together these two concepts, you have self-referencing systems. A formal system can define itself recursively. The first formal examples were given by this guy, Kurt Gödel. He proved in 1931 that arithmetics can express itself. So you can translate any arithmetical theorem into a theorem about numbers, so into an arithmetical statement. So arithmetics can study itself. Here is the sketch of the celebrated incompleteness theorem, which says that there exists a true theorem in the arithmetics which is not provable. So there are more truths than than the provable ones. Okay, if you install a formal system for the arithmetics, it could never be so powerful to catch all the truth of arithmetics. This is the so-called incompleteness theorem, and the very idea of this theorem is to express arithmetical truth of a formal system in itself, to use the self-description of the formal system. Of course, this self-reference gives a theorem analogous to Gödel theorems also for computer science. For instance, this is a theorem of Turing, but the trick I show you was invented by Christopher Strachey, another great computer scientist, British computer scientist. Imagine there is an h of s function, JavaScript function, which takes another function s in input and return true if the function does not go in infinite loop. Because a function, when you call a function, it can contain an infinite loop and never terminate. So the function h decides if the function else terminates or not. If it terminates, it returns true. Else it returns false. Such function h cannot exist. Otherwise, I could write this foo function, which computes h on foo itself. If the returned value is true, which means that foo terminates, then it enters an infinite loop. So it doesn't terminate. But if the value of h on foo is false, so if foo does not terminate, you see that foo doesn't execute a while loop, so it terminates. So if h would exist, you could write a function which terminates and doesn't terminate at the same time. So that's impossible. These are the kind of things that happen when a system can describe itself, when a language can describe itself. This is the whole halting problem. I think most of you have studied this stuff in theoretical computer science. But here we see, it's wonderful that we see a JavaScript program that cannot exist, actually. That's nice. This was Corrado Böhm. He was an Italian computer scientist, and he taught in Rome University. He wrote in 1954, he was at the ETH in Zurich. He did his PhD thesis invented the language and wrote the interpreter for the language and the language itself. And this is the scheme of the interpreter. I think this is one of the first self-interpreting languages, one of the first examples of metacompilers. Then we have, of course, the celebrated self-implementation of Lisp. This is very famous. Was given by McCarthy. Actually, McCarthy didn't invent Lisp as a programming language. He invented Lisp as a formal notation to express functions. Then one of his collaborators coded by hand the interpreter in machine language, so they got an interpreter for the Lisp. So it became a programming language by accident, let's say. That's very famous. And there are many other examples. This is very clever. This is a language to describe other languages, and that's the description of the language in itself. This is called Meta2. Was invented in the 60s to help the writing of compilers. So we have a long history of self-interpreting, self-compiling languages. Now, of course, since the power of any language is equal to the power of any other one, all programming languages have the same power because they all have the same power of a Turing machine. Okay, so they are equally powerful. They can be more expressive than others. You can express more easily in something in C++ than in Fortran, but the computational power is the same, because they can be but translated into machine language. So any programming language, in the end, is equivalent to machine language. Okay. And so any language can be can implement itself, because you can write a compiler, for instance, for the C++ language in C, and then you can write a compiler for C in C++, so you close the loop and you have a self-compiling C compiler. So my principle, aesthetic principle is this, according to me. The more a language can implement itself in simple and natural way, the more it's elegant. Because, guys, all the stuff I show you are very elegant stuff. Gödel theorem, the non-existing function of Turing. These are, of course, elegant. I think no one in this room can say, no, that's boring, that's not interesting. They are very elegant concepts. And they are tied to the fact that the language can express itself. So I think that the more easier is for a language to implement itself, the more the language, in some sense, is elegant. So I want to show that JavaScript is elegant, and to me, it's elegant. To do that, I wrote more than 10 years ago this interpreter. It's actually some sort of compiler. I will show you the code after. And but let's first see why JavaScript is such a great idea. JavaScript is a crossroads. It takes great ideas from the past. For example, it takes the idea to have function as objects, which is one of the interesting things in JavaScript, is that functions are objects of particular kind. It's taken by the Norwegian language Simula. Simula 67 was the first language ever with classes, invented in the 60s by Dale Nygaard in Norway. And it takes the syntax from C, the curly brackets, most keywords, because it wants to be a familiar language to the programmer of the time, which were used to C and C++. It takes first-class functions, which now it's okay, any language has this feature, but at the time was not so common. And it takes this feature from Scheme, because Brendan Eich was a programmer in Scheme. And then takes the part of the name from Java. I think the only thing it took from Java is, I think it was just a market operation. Okay. Anyway, you see, guys, I'm sold that I remember when this language come up. I remember the time where there was no JavaScript. Believe it or not, there was a time. I remember the time where, more or less at the same time, Java, Python, and JavaScript were defined and became to be used, okay? More or less in the early 90s. Before that time, you only had C++ and Java. Well, C++, okay? The only object-oriented language C++ aside was Smalltalk, which was not so diffused. It was very difficult to grasp. So I think JavaScript was a great revolution. And it ran inside the browser. Okay, that's another feature, very interesting feature, in the early 90s. Okay, so I took a subset of JavaScript, which was more or less the JavaScript of the 2013. So no arrow functions, no promises, no async, of course. But I took this subset. Here is a grammar of this subset of the language, and trying to implement it in itself. So let's see how to build a compiler from scratch. How can you do that? Well, in Java, it's quite easy, but it's a process which has some difficult parts. You need to be Darth Vader to do that. Some easier part, just a stormtrooper can do that. And the easy part is the so-called scanner. The scanner takes an input, the text of the program, the source code, and perform the tokenization of the code. Next, these tokens go into the compiler, which produce the code and runtime stuff. Then you have the runtime environment to execute the code and the runtime stuff. If you're using virtual machine, you have to program the virtual machine, but that's not so difficult because usually one chooses a very easy virtual machine. So in JavaScript, you just have to write 3 functions. Scan, which takes a string, returns, let's say, an object containing the tokenization. You feed compile, another function with this tokenization. The compiler returns an object containing the code and all the runtime stuff. And then you write a function run, which just executes the code. Okay. So we have to write 3 functions. Let's see more in details. The scanner takes a text and returns a list of tokens. A token is, okay, you have to represent the token. For instance, if it is an identifier, you want the name itself of the identifier. Then you take an enumerate type, let's say enum type t, which say if it is a number, a string, or whatever. And then you identify the coordinates of the token inside the text, typically the line number and the column number in which the token occurs. That's mainly for debug reasons or to print an error message which is not there is some error, but there is an error in that point of the source code. Then the actual compiler takes in input the token list and returns an environment and an object which contains several stuff. I will explain later this kind of runtime environment. I took it from a classical implementation. I will talk about this later. Of course, I will show you a very Neanderthal code because it's just one huge file which uses a very poor JavaScript. Why? Because I wanted the compiler I wanted to compile the compiler by itself. So I had to write in the code I was able to compile. I didn't use the full power of JavaScript. I used only the subset I selected. Okay. So don't do this at home. Please, software engineers, close your eyes because this is a bad engineering program. It's just a monolithic piece of code containing a bunch of functions which do the things I explained before. The runtime engine is very easy. I've chosen a stack machine because it's a tradition to do so. They are very easy to deal with. Stack machines has a long history, much before than Java. Java is credited to use bytecode, stack machine bytecode, but actually in the 60s there were stack machines with bytecode. I want to take some moment to price stack machines. They are beautiful, and to price stacks in general. It's the most fundamental data structure in computer science. Stacks were invented by Turing. When he built the first computer in Liverpool, the first European computer in Liverpool, he understood that he needed a stack to keep track of return addresses of subroutines. So stacks were invented by Turing for this very reason. Next, in the 60s, they built virtual stack interpreters for programming languages. At the time, there were 2 such implementation. Peter Landin virtual machine for Lambda calculus, and Dijkstra virtual machine for Algol 60. Algol 60 was the C of the 60s, was the most simple and expressive language at the time. And next, the top of the stack machine was the Forth language invented by Chuck Moore in the late 60s. So stack machines are a classical concept, are very easy to implement, are very efficient, and all they need is a stack. Actually, you remember the correspondence between automata and languages. One can prove that to parse any programming languages, a single CPU with 2 stacks will suffice. It's not needed a complete Turing machine, but a single CPU with 2 stacks. This guy was Peter Landin. He wrote a paper in 1963, The Mechanical Evaluation of Expressions, in which he showed how to implement any pure functional language. So since JavaScript has a functional part, functional flavor, because of the Lambda function as first citizen stuff, I used his machine to implement JavaScript. So this is very classical. This machine at runtime has one stack to keep track of values. For instance, if you evaluate an expression, temporary values are pushed on this stack. Then it has a list of environment. An environment is just a JavaScript object which is used to store variables. Keys are the names of the variables, and values are the values of the variables. You maintain a list of nested environments to keep track of the nested calls of functions, and that could handle also recursive calls because we are using a stack. Then we have the list with the actual code to execute, and then a dump stack, which is to perform some householding stuffs. It's not strictly needed, but I use it because it is in landing paper. So stack machines usually employ bytecode, but I want to compile JavaScript so in itself. So the bytecode will be JavaScript functions. So the code to execute will be a list of JavaScript functions. Then I have a pointer, a variable which addresses the next instruction to execute, fetch the function, execute it, and go on. From time to time, instead of the function, you can find there a value. For instance, if you have jumps, you will see that in a moment later. For example, this expression, 1 + 2 × 3, is compiled in the following way. You got this operator push, which hits a number and push on the stack. So we push 1, push 2, push 3. Then we have the multiplication operator, which retrieves the two topmost elements of the stack, multiplies them, and push the result on the stack. And finally, we apply the add operator, the add function, which retrieves the two topmost elements on the stack and make the sum. And the result is the one I show you there. Hereinafter, I will show you an example. To compile instructions, I use the so-called top-down parsing. There are two kinds of, if you want to implement a language, you have two ways. Top-down parsing, bottom-up parsing. Top-down parsing means the following. You take the grammar of the language. For instance, here, you have expression, you see? An expression is a prefix operator optional, followed by a value, possibly followed by binary operators and other expressions, okay? So each definition gives rise to a function, okay? So there will be a function expression, which first of all invokes the function for the prefix operator, and so on. So you translate the grammar productions, the grammar equation, into function calls. And you proceed top-down, from the topmost elements of the grammar, so down to the language. This technique I use for compiling instructions. And you imagine the structure of the compiler more or less. To implement control instructions, we will use jumps, because we are on in a very low-level machine. Now I want you to show instead how I parse expressions and evaluate them inside the compiler. In this case, I use bottom-up technique, which is more efficient. It requires two stacks. Let's take, for instance, that expression written there, 1 + x × x - 1. I want to write the code for the virtual machine in the array C, initially empty, and I use a stack S to keep track of values, of operators. So I parse from left to right. So the first thing I parse is the 1. Since it is a constant, I compile it on the code. Actually, it will compile push 1. Remember, the instruction will push at runtime the number on the stack. Next, I parse the plus operator. Since it is an operator, I push it on the stack S, and I go on. Then I have x. X is a value, and I compile it into the code. Next, I have a star operator, multiplication. Now, since multiplication has higher priority than addition, I put it on the stack. On the other case, I will compile the top of the stack in the code. But in this case, I accumulate it on the stack. I go on. There is an open parenthesis. I push on the stack. Next, I find X, and I compile in the code. So for the moment, the code contains only values, a constant and 2 instances of variable. Then the minus operator, sorry, I push it on the stack, then 1, and then the final closing operator. Now, since the expression is ended, I take the element on the stack S and pop them and push on the stack C. And the result is this one. So the sequence of instruction is 1, X, X1, minus, times, plus. Now, I show you that I can evaluate very easily this stack, this list, to provide the correct result for the expression above. This is done in this case. Let us suppose we are working in an environment in which the value of X is 2. Of course, X should have a value, otherwise I cannot evaluate nothing. So I start from the compiled code. So the first thing I execute is 1. 1 push itself on the stack. Now I am at runtime. Before I was at compile time. Now I am at runtime, and S is the runtime stack. I am evaluating, executing the code. So 1 is pushed on the stack. Then X, I retrieve the value, which is 2, and I push it on the stack. I do the same thing for the other X, for the 1. Then I execute minus. Minus take the 2 topmost elements of the stack, which are 1 and 2, perform the subtraction, and push the result on the stack. So 2 minus 1 is 1. Next, I have the multiplication operator, which takes the 2 topmost elements, perform the multiplication, and so I have 1 and 2. And finally, the plus operator, which performs the sum. So in the end, I'm left with just a value on the stack. That's the result of the expression. This is very efficient at runtime, and it's also very easy to be implemented at compile time. So these are actually the 2 techniques I used. Now I want to show you, let me see. Okay, since I'm old, I told you I'm very old. I produced an old-fashioned system. Let's, for example, load some. I provide some test example. For example, an example of closure. Okay, this is a simple example of closure in JavaScript. We define a function f. Inside the function f, we define a function g, which takes one parameter y and uses the parameter x of the outer function. Then we return g. This is an example of closure, because JavaScript doesn't erase the environment of function f because it is needed by function g. So let me run this program. Okay. So I ask, now I run the program not with the JavaScript engine of the browser, but with my compiler. And you see, in the first place, you see an array, which is just the function f. In the second line, you see another array, which is the function g. And in the third line, you see the evaluation of f on 10, which is a function g. And then I evaluate g on 20. So I get 10 plus 20, 30. That's the result, okay? If you want to see the compilation of this program, this is the compiled code. This is the actual compiled code according to the language of the stack machine. So the compiler do the following: compiles the code and then execute it. And it's very efficient in executing it. Now I'm printing labels, but actually any one of those capital label is a call to a JavaScript function. So it's very efficient, the computation. This is just an example of, okay, voila. And if you wanted to see the code, I open, perhaps better if I open it in a more modern, okay. This is the code of the compiler. It is just a bunch of functions. There are 1,200 lines of code, and the code is very easy because these are the implementations of the actual commands of the stack machine. The parser is this one, the compilation functions, and the scanner is this one. Okay, I wrote the scanner by hands without using regular expressions because it's more fun. There is more fun. No, it's nice because, you know how a regular expression is evaluated. Since the time of Ken Thompson. Ken Thompson is the guy who invented Unix. He also invented grep. He wrote the grep program. So the regular expression is compiled to an inner form, to a finite state machine. And then you feed the finite state machine with the expression you want to match. Okay? So I wrote directly the finite state machine, which is this one. Okay? Just some if, some while. It's very, very easy. Okay? So the compiler can compile itself. I can, let's see this, and then I terminate. I can compile, oops. Okay. Sorry, but I'm doing anything in the browser. Okay. This is the code of the compiled compiler. You see, it's okay. I don't enter into more details. If you want to get some fun or to modify, to do whatever thing you want to do with my code, even throw it away, you can. Let me. Okay. You can find it here. Okay? Because this is a self-referencing presentation. These QR codes carry you to the presentation itself. I thank you very much. Thank the organizer. Have a nice return.